Okay, so now the idea will be we're going to use Fano's inequality to prove the converse of the channel coding theorem. So Fano's inequality is actually quite unexpected, or perhaps it's not super unexpected that uncertainty would have to do with probability of error, but it's kind of neat that I mean, we've shown that certain properties of entropy, such as mutual information, cause the probability of error to go to 0. But it's neat to see that there's some specific relationship when probability of error doesn't necessarily go to 0 between entropy and probability of error. Now, this is the setup we're going to use. So remember, the channel coding theorem setup, roughly speaking, looks like this. We have messages going in here from a set W. We have an encoding function which leads to some vector x1 to n. So that's the encoder. And we have a channel from of f y1 to n given x1 to n, which produces y1 to n. And then at the output, or excuse me, those channel outputs are fed to a decoder with this function g, which spits out w hat. And then an error occurs if w hat is not equal to w. So on this setup, Fano's inequality states that the entropy of the message set, or the messages, given the channel outputs. So remember what Fano's inequality said. Let me write it at the top. And this will be the weak form of Fano's inequality. H of x given y is less than or equal to 1 plus p log cardinality Sx plus 1. Excuse me, minus 1. Excuse me, we can weaken this further. I should have mentioned this a second ago. Because log is monotonic, if I add 1 to this, that's still an upper bound. So this is further less than or equal to 1 plus PE log cardinality Sx. So that's the weakest possible form of Fano's inequality, but it's still true. Okay, so on this setup, Fano's inequality, if we treat from there to there as the channel, and we agree that, okay, so the channel input is from a set W, the channel output is some vector, but if we treat those vectors as individual discrete symbols, there's not really a problem. Then the conditional entropy of the channel inputs given the channel outputs is less than or equal to 1 plus PEN times the cardinality of the message set. Now PEN, that is specifically a notation that I introduced probably a couple of weeks ago, and that is the average probability of error. everything sort of makes sense here. This is the PE was the probability that the output, excuse me, that the function of the output was not equal to the input. Now this is average because once again we have in mind the average code book, and so therefore we're averaging over all the possible code books, so therefore this is average. So you'll remember when we started proving the channel coding theorem last time, we ended up with the average. We ended up starting out with everything phrased in terms of the average probability of error, and then at the end we had to go through some arguments to translate that into the worst case probability of error. But here we're going to start with the average once again. Now, what is cardinality of W?
The code line.
It's no, it's actually the number of code words. So we had a sequence. We were arguing that there was a sequence of n to the nr codes, meaning this is the code length, and that's the number of available code words. So what's the cardinality of W?
2 to the nr.
It's 2 to the nr. Wait. Sorry, my bad. Should be log cardinality of W. So yeah, it's log to the nr, which is what? It's nr. So this is less than or equal to 1 plus PE nr. Note that if I have vectors x1 to n and y1 to n in a discrete memoryless channel, this is equal to h of x1 to n plus h of y1 to n minus h of x1 to n and y1 to n. Now, in a discrete memoryless channel, all of these are all IID. All of x, y, and x jointly between x and y are IID. So therefore, this is equal to nh of x plus nh of y minus nh of x and y. Which is equal to n times h of x plus h of y minus h of x and y, which is equal to n times the mutual information. So all of this is intuitive. If I take mutual information between two vectors of length n in a discrete memoryless channel, then it's just n times the mutual information of any individual channel use, because all the channel uses are the same. But furthermore, it makes sense that n times I, x, and y is less than or equal to n times the capacity, because mutual information, or excuse me, capacity is the maximum of mutual information. So that's what I wanted to show. Basically,